Now we'll transition to the second talk for LiDong, who's going to talk on generative pre-training of image and multimodal transformers. Li, are you there?
Yes, I'm here.
Can you share the screen just to make sure we can see you?
Sure,
Okay.
I have shared the screen.
Okay, yeah, we can see your slide. So Lee is a senior researcher at Microsoft Research. His research focuses on large-scale self-supervised learning across tasks, languages, and modalities. His research has been recognized through a number of awards, including the ACL Best Paper Honorable Mention and the AAAI Best Paper Runner-Up. And today he will give us a presentation on generative pre-training of image and multimodal transformers towards the path of reaching the birth moment in computer vision. So the stage is all yours.
Okay. Thanks for the introduction. Hello everyone. My name is LiDong. I'm from Microsoft Research. Today my talk is about the generative pre-training of image and multimodal transformers. As we all know, there is a new AI paradigm, which is self-supervised pre-trained models. So the whole pipeline is as shown in the slides. So for the first step, we collect a large amount of onboard data to pre-train the model. And for the downstream tasks, we just append some task layers and use very few labeled data to fine-tune the model, and then we can evaluate the model. And this paradigm has been very successful across different areas. For example, for the natural language processing, for the vision and the speech and the multimodal areas. So as we can see in the past year, the first trend is that the model has become larger and larger, and we can see a very clear trend for the in the natural language processing and also in the vision area. As the first talk, the vision transformer is also scaled up to very large size for better performance. And the second trend we would like to talk about today is the convergency. The convergency is for all the areas. The first reason is that the transformer has become the de facto backbone network across different areas, and the self-supervised pre-training tasks are also converging. For example, for the generative pre-training, is from the language to the vision and the speech area. And for the contrastive learning, it's also very popular in natural language processing area now. So we think that one of the key milestones is the convergence of the natural language and the computer vision areas, so that we can have a very multimodal pre-trained model. So when we first work on this problem, we found that actually it's the current the previous pre-training method is not that successful, especially when we scale up the model size. So when we analysis the problem, we found that actually for different areas we use different pre-training algorithms. So our thought was whether we can translate the success from language to vision. So as we can see, for the backbone network, in the natural language processing area, the transformer has been the dominant backbone network architecture. Almost all the successful models are using the transformers. And in the computer vision area, the VIT is also very successful. But for the self-supervised pre-training methods, for the language area, the most successful task is the masked language modeling. And in the vision area, it was almost all the papers are focusing on the contrastive learning. So we will think about whether we could propose a similar pre-training task which is similar to the BERT pre-training in the NLP. So we call it the bait pre-training of the image transformers, which is named as the bait, which uses the masked image modeling. So let's talk about the bait pre-training as shown in the slides. So for a pre-trained model, there were three parts. The first one is the data, and the second one is the model, and the last one is the pre-training task. So for the data here, we just use the annotated images, and for the model, we use the vision transformer, and the task is the masked image modeling. So because for the data is quite clear, so let's talk about the model first. So for the model, we use the vision transformer here. The reason we like the vision transformer is because it's simple, and it's also very scalable in the as shown in the previous language work. And it's very suitable for the scaling up, because we have trained so many large language models. We can directly borrow the experience to pre-train the vision transformers. So for the vision transformers, there are two key elements. The first one is self-attention, and the second one is the feed-forward network. So let's look at the first key element in the vision transformer to see why the transformer is so suitable for the pre-training. So for the self-attention, we can view it as a message passing process. So it's like we have so many tokens or something like words or image patches, so that we can use self-attention to propagate the messages between the tokens. The self-attention mechanism was proposed during my PhD study. So at first, our motivation was to apply the neural network for the natural language inference. So we thought whether we could build some mechanism for a sentence so that it can propagate the information between different tokens. That's why we introduced the self-attention. So as shown in the slide, in our original paper, we call it as the intro attention and the inter attention, and the inter attention is cross attention now, and the intro attention is self attention here. And then Google's researchers successfully applied to the to build the transformer. Actually, we also tried to apply the similar technique to sequence learning tasks, but we didn't do it very successfully. Maybe because of the some architecture differences, but it actually works very well for the encoder, especially for the natural language inference. So after we look at the first component, the self-attention, actually the second one, the feed-forward network, which is often ignored by most people, but we think actually this module is very important for the large-scale model. The reason is as shown in the in this picture. As we can find that actually we can view the feed-forward network as a key value database. So let's look at the red figure. So for the first layer of the FFN, we can treat it. We can treat all the parameter vectors as a k vector, and the activation function we can view them as some gate to whether the query vector will trigger the k vector, and then and for the second layer of the feedforward network, it can be viewed as a value vector. So if we look at this, it's actually very similar to a neutral version of the key value database. So that's why we can scale up the transformers to such large scale. Actually, most parameters are in the FFN layer rather than instead of the self-attention layer. So we can use these neurals to increase the capacity of the whole network. So after we have these two blocks, I think another successful ingredient of the transformer is very stable to for the pre-training. So in our work, we showed that actually we can stack up to the 1,000 layers of transformers for our task. It can be stably trained from scratch. So that's why we think the transformer is very powerful for the pre-training. So after we look at the architecture, it looks very good now. Yeah, but if we directly use supervised pre-training for the vision transformer, we can look at this figure. We can find that after we increase the model size, there is an annotation bottleneck for the large size model. If we keep the data size as the same, if the data is larger than the model, we can get better performance by increasing the model size. But after a certain point, if there is an annotation hunger issue here, the data is not enough to continue to improve the performance. So in our preliminary experiments, we first try the contrastive learning in computer vision, because most previous work are using this. So we first try this. Yeah, but we found that actually it has some performance saturation issues here, especially for larger size models. We found that if we increase the model size and if we also increase the training epochs, we found that the performance become quite similar. It's quite dissimilar as in the natural language model pre-training, where we can increase the performance by training more steps. And another issue we found is that it's not that easy to scale it up, because we need multiple pass encoding, and also with the large batch size, which needs an expensive memory, and also heavily rely on the data computation. Yeah, so then we try to leverage the successful idea from the naturalist called the masked language modeling to transfer it to the image to the vision area, which is called the masked image modeling. So here we are going to introduce the base pre-training. So first I would like to describe the visual tokens used in our work. So for the visual token, actually, it's a very simple idea, which was also introduced in the previous talk. So the key idea is here is to tokenize an image to some discrete tokens, which is quite similar to a sentence. So for the input image, our training task is to recover the original image, but there is a discrete bottleneck there, so that we can learn a tokenizer to summarize the original input to some tokens. So after we get the visual token as one view for the original image, we have another view, which is the image patch view. For the image patch view, it will be used in the pre-training and fine-tuning as the input, and for the visual tokens, they are used as the output. So after we have the image patch, in the first step, we do some blockwise masking to mask some image patches for each time, and repeat this process again and again until we mask a certain. And for this image masked patches, we have the corresponding visual tokens. And then we flatten all the image patches and replace the masked patches with a special token, and input them to the transformer encoder. After we get their representations, we use a softmax classifier the corresponding tokens, where the objective is to maximize the log likelihood of all the masked tokens. So this is the whole process of the pre-training. We also here we show that we can view the bit pre-training from the perspective of the variational autoencoder. So let's consider the evidence lower bound of the image reconstruction. So look at the able, the first term of the able. So for the first term, actually is the visual tokenizer training process. So for each image, we can sample some visual tokens and to recover the original image. And for the second term, we can find that actually is a masked image modeling process. So that's why we can also view the bit pre-training as the image reconstruction in the pixel level. So after we pre-train the model, it's quite simple to apply the pre-trained model on downstream tasks. We just pinned some very lightweight task layers upon the encoder, and then randomly initialize the task layer and fine-tune the model end to end. For example, for the image classification, we just need to append a very simple softmax classifier, and for other tasks, it's also very similar. Yeah, so let's look at the results. First, let's look at the image classification results. The dashed line shows the vision transformer large trained from scratch, and we can the other line is the base large model. We can find that for the large size model, we can significantly reduce the requirement of labeled data by more than 200 times. And if we increase the number of annotated images to the 70 million, we found that we can further improve the performance on downstream tasks. So then we can find that the bit actually overcomes annotation hungry for computer vision quite a lot. And also we also show the performance on the semantic segmentation. It also improves over the previous strong baseline. Besides the good performance, we also found that the pre-training improves the convergence speed quite a lot, which is a good property on the downstream tasks, because we can after we pre-train the model, actually we can save the computation cost when we utilize them. We can use a very small fine-tuning epochs to get a decent performance. And in our observation, we also we found that as long as the model size becomes larger, this fine-tuning epochs can be reduced to very few. But this is still larger than the compared with the pre-trained language models, which only need several epochs in the real world applications. And we also analysis the self-attention map learned by the pre-trained base. Although without any manual annotations, we can find that such self-supervised learning can learn the concept of objects and some boundaries. I think that's why it can improve the performance on downstream tasks by leveraging the masked image modeling. So as we described, after we get the unify the pre-training task for the vision and the language, actually we can extend the idea to the multimodal pre-training. So here, as we show in the slides in the left, we modify the vanilla transformer to some kind of like the MOE model. So for different modality, there is a hard switch between different experts to switch to use different FFN block, and for different data, for example, for the text, we can use the masked language modeling, and for the image, we can use the masked image modeling, and for the image and the text pairs, we can use a masked vision language modeling. After using this, we can use one transformer and one objective to pre-train for the visual language, to pre-train a visual language model to get quite good number. And beyond this, as we talked before, there is a big convergence in terms of the model architectures and the pre-training tasks. However, these models are still modality specific or task specific. So our prediction is that there should be there would be more aggressive models to get some general purpose capabilities. Such as very recent works like Flamingo, Pixel 2Seq, and the UVIM just introduced in the first talk, and also the unified I/O from AI2. As shown in the slides, we can build a general purpose interface, which can be used as something like a language model to access different kinds of pre-trained models, such as for the language and vision. So we can reuse all the capabilities learned from the language model, such as the fine-tuning or in-context learning to do some few shots learning, and we think that it should be after the big convergence, there should be more opportunities for different areas to work on this. So in summary, Okay. Our method translates the success from the language to vision, which introduced the masked image modeling task, and we can achieve strong fine-tuning performance on downstream tasks, and it's also very scaling up friendly to pre-train a very large-scale model, and we can overcome the performance saturation compared with the contrastive learning. After we unify all the pre-training objectives, we can get other good multimodal pre-training algorithms, which greatly reduces the reliance on image-text pairs. Okay, that's the talk today. Thank you.
Let's thank the speaker for the excellent talk. Okay, any questions? Yeah, for those of you who have questions, please come to the mics.
Very nice talk. Thanks a lot. Couple of quick questions. How you differentiate yourself from patch level distillation, be it supervised or unsupervised? And secondly, tokenizing, whether the tokenizing would limit the performance in terms of that you are trying to map essentially what you have in your pre-trained encoder.
Mm-hmm. Okay, so for the first question, actually I think it's a very good question. So actually we compared the direct distillation in our paper, and the distillation result actually is much worse compared with the masked image modeling. So I guess the most important part here is to include the masking. So with the masking, the model can learn to recover the original image instead rather than just distillation. And for the second question, I think for the masked image modeling here, we can have another view for the problem. Is some kind of masked distillation here. So the key point is here the model can perform much better than the so-called teacher model, or called tokenizer here. So if we have some very worse tokenizer here, I think it might also make the pre-training performance worse. But I think the more interesting part here is there should be some more theoretical analysis to show what kind of tokenizer model here, or the teacher model here, is what we lack, and what's the desired property is here, so that we can further improve the pre-training performance.
Thanks. Okay, and then maybe let's take one question from the virtual audience. So could you detail a bit more about why P4 networks and transformer layer can be viewed as a knowledge-based modeling, and why this part can be especially adaptive for obtaining mixture of experts with a single model?
Okay, sure. So for the thanks for the great question. So let's look at the second figure here. So this is the feed-forward network block here. So the input to it is a hidden state. We can view it as a query vector here. And for the first layer of the feed-forward network here, for each column vector, because the first step is we do the inner product between them. So we can if we view them as the key vectors. So for the first step is we will match the hidden states with each k vector. And after we match them, get the score, we will input them to the activation function. If one column vector is activated, we will trigger the corresponding value vector, which is the second layer in the feed-forward network, and we do a weighted sum here to get the output. That's why we can view them as the key value database. So the whole process is we query the hidden state vector here and to match the key value vector here and to get the output. That's why we can view it as a database.
Okay. Yeah. So unfortunately, we don't have any more time for questions.